Okay, so this lecture is going to be about fast networking. I'm going to break this up probably into two parts, where we're going to talk a little bit about the theory and structure of how we're going to do the networking, and then we'll look specifically at the way Unity and Unreal enable networking, or what options there are to do the networking in those systems. But we'll start first with just a presentation of how this is generally done. Um, so I'll start first by just defining the difference between what I mean by fast networking versus, say, slow or massive networking. That's really the difference between, say, an FPS and an MMO, right? And so on the fast side, which is to the left here, we're worried about low latencies and lag. We're worried about having responsiveness of the game, feeling like it's an action game usually. Um, there are lots of updates, lots of packets per player, and usually you have an upper player limit, right? You actually have an upper player limit in both, but it's much larger in the massive case, obviously. So in the massive case, and so the upper player limit, as we'll see, is really to control the amount of data that you're either needing to download or generally needing to deal with in terms of the bandwidth. So in the massive case, there are a lot of players. At this point, we maybe no longer care about how latent it is, because what we really care about in most massive games is just having lots of players. And so we have to give up on being able to send all the data all the time that we would want to send normally. So there are fewer updates. We'll usually do level of detail on the networking. It's very closer. It's much closer to turn-based, where um, we'll allow the players to sort of make turns, or we'll do some trade-offs and say make smaller instances where now we're maybe doing a fast networking style or closer to fast networking style in these smaller instances, but we have an upper player limit of, say, 64, 128 or something like that, where we control it a little better. We still don't have the level of detail in terms of the kinds of things you see from like a fast game. But more and more, especially as networks are getting better, uh, this kind of distinction is blurring quite a bit. And so there's a lot of games that are doing like closer to massively multiplayer FPS and things like that. So when you're seeing those kinds of things, you're probably still seeing instancing to some degree, but it is certainly getting closer, I guess, in that sense. The other thing, one of the other trade-offs is that a lot of the massive multiplayer games, because you're not worried about latency, you're maybe more worried about, well, some of the things that we talked about in the first semester, the intro semester, about the things that players care about. And some players actually care about socializing more or showing off their stuff. And so a lot of the games, the MMOs, are about acquiring cool gear and then being able to show that off. And so having that level of individuality means you require that much more network communication to talk about your player's state, but you're willing to take that trade-off in order to let the players focus, right? So there's a trade in terms of what you're using the networking for. So the player individuality in this case is like customizing the way your player looks or what they're wearing or how cool their equipment is, because that's one of those things that you do put into a massive game. And so since you're slowing the networking, you can afford to send all that extra data. In the case of other games where you've got skins and things like that, say in League of Legends, they really do all of that setting up front. So they sort of download it, and the only thing that on your side is sort of a selector, a simple selector to say what skin they're actually going to end up presenting on the other end. But you've probably already got the data on your side. You just may not have the ability to unlock it yourself if you didn't pay for it, for instance. Okay, so there are two ways to think about fast networking. One is essentially FPS style, and the other is RTS. There are some ways to blend these, but usually you do one or the other. And the breakdown is in terms of what kinds of data you're sending. So in the case of the FPS, the sort of data you're sending is more information about your body position, very precise information about your location, because somebody's going to need to shoot at your location, or they just need to know where you precisely are. So even if you're not necessarily doing an FPS, but you are co-op and you care a lot about where the other person is at a particular moment, you will probably want to do the FPS style in that case. It's also the case where you really only have, say, one individual or one thing that the player is controlling around one person, one character. In that case, you might as well do the FPS style, because now you can get very precise information about where that other player is. So a co-op game or even a platformer, you can get really precise information about where the other player is, and kind of pull that capability out. There's something to be said that I'm not going to address, say, trying to do a Mario co-op or a Street Fighter combat game as similar. It's probably close to the precise body information position, but your latency issues are worse in some of those cases, because if you're, say, trying to jump on a player's head or trying to time like a kick to their head, the latency might actually be even worse, because you're really close and the timing is very precise about blocks and all that kind of stuff. So I'm not really going to address that here, but it would be closer on the FPS side, and even more precise probably than what we're going to talk about here, which does allow for some slippage into lag. The other version, so that's FPS, and we will go over what the asynchronous and rollback looks like, and how we go about trying to get that precise location. And that's really what I'll show in the two engines. I'm not going to try to show the RTS. The RTS version is simpler in some cases, except for one major point, and we'll get to that. So if you understand the networking, you can probably do the networking side of an RTS pretty straightforwardly, just given the same kind of networking system that you would use for an FPS. But the huge difference is what we'll talk about in a minute. And there, in an RTS style game, your player is controlling far more units, right? So it's not just an individual unit; it is many units, and so instead of having precise positions about those units, you're actually more interested in, maybe where they're positioned in space to a good degree, but you are probably selecting a large army and saying, I want that army to move over here. And as long as both sides agree about where individual units are, you don't necessarily care that you've moved this unit like exactly 0.5 units away, or 0.5 meters away from where it was currently standing. You just kind of want to move your army over here or over there in those kinds of terms, or moving them away or close, right? And the idea, is that your units are all taking care of their own intelligence in terms of trying to shoot the bad guys, and how precisely they're aiming. Really what it ends up being is that they're going to do some kind of damage over time, right? Damage per second to another unit. And so that unit's going to drain hit points, or they're going to do maybe some areas of effects. They're going to hit a large quantity of people, and so it does matter maybe how those people are positioned, but you don't care that they're very precisely positioned, or you're sending new commands to try to update their position a little bit. But there is a lot of that, right? So there's a lot of things happening, a lot of commands coming through, and so the difference there is that we do a synchronized networking with determinism in the simulation based on that. And so let's break that down. Let's start with the RTS, and then we'll break down the FPS next. If you've not heard of this boom headshot phrase, then you should certainly, or maybe you have, but there's an origin to that is worth investigating. I'm not going to tell you here, but I will leave it to you to learn about and then dig into that particular rabbit hole. But certainly try to find the original location of it, not just where it might be on say, Reddit or something like that. Anyway, moving on. So let's get into first the RTS version, which again is the synchronous and deterministic phase. So it's fairly straightforward, which is why we'll start here. And then we'll move on to asynchronous and FPS. So the straightforward part is the networking. So really what we're doing is we're sending commands, okay? And we're doing this where so you see this first block here, the flow chart. We send the commands, then we wait for everybody to respond. This is in real time, but we're still waiting for everyone to respond. If they don't within a certain amount of time, and the amount of time is around 100 to 200 milliseconds, then we start to desync and we worry about things breaking or whatever. However, if everybody responds within that window, then we process our commands, and then we increment our turn and start over again. Okay, so it's very straightforward. The key factor here is that we really are only sending commands. So this is in the form of things like the group movements, where we want to send our units. We'll even go down to the level of selection. So when you do a selection, you're of course dragging a box on the screen. What we'd probably send across is actually something more like the collision with the ground or a box that is drawn along the terrain that you're selecting. And the idea there is that everyone else is going to do exactly the same selection that you're sending across with exactly the same units that you have. So everybody's computer is simulating the entire game. And it's almost like one computer has, say, 8 keyboards attached to it, 8 keyboards, 8 mouse. And each of those keyboards and mouse is only controlling a subset of all the units in the game, but they're controlling their units. And so when you're sending those commands, you are simulating exactly the same commands that the person did on their side. So you're simulating all the selections, all the build queue commands, all the group unit moves. And the idea is that by only sending the commands, you really don't have to send that much data. In fact, you're doing this quick enough that you really only send one command. So you only have time to say, do one selection, or you only have time to say, set up one build queue. And you might think, if the window is large enough, then I could send multiple commands. But most people, at the highest end of, say, StarCraft, only do about 300 actions per minute. And 300 actions per minute only translates to 5 actions per second, which is around 200 milliseconds. So if we're somewhere on the order of 100 milliseconds between each of these turns, you really can only send one command. And in some cases, you might actually send no command. So the other one that's kind of a default is that the command that you'll always send is a no-op. Right? So if you don't send anything else, if you've done nothing for that particular turn, that real-time turn, for lack of a better word, then you will send a no-op to say, I'm not doing anything. And so it moves through. And it turns out that this works really well, and this has actually been the case ever since this article, this 1500 Archers on a 28.8 modem, was written like 30 years ago now, or 25 years ago, or whatever it is. And so that was a long time ago, with the networking much worse. And yet this whole technique essentially has continued for the case where you're using large armies. Now it's possible to start diverging from that because our networks are getting better. But if the technique works this well, we can stick with it. Now the problem that we run into is that when we go to process the commands, everyone has to have exactly the same result. And if you remember when we've talked about things like physics and floating point values, that's actually hard to do because we accumulate error, right? And not everybody accumulates error equally. So if I am relying on the fact that I'm only going to send a selection box and I'm not going to tell you specifically which units I'm trying to send, if you have a unit that's even, say, 0.5 meters off from where I think the unit is, or whatever the size is, my selection box might, on your machine, might miss that character. Even though I selected him on my machine, you missed him on your machine, and when you send the command, that character is now out of sync. Because all we're sending is the selection, and then later when we send the group move, we say, I'm just sending everybody that I selected off. I don't actually send individual commands for each of those units, because again, I could be selecting like 100 units to move at once. And so rather than sending 100 move commands, I send one move command for the entire selected group. And what this boils down to is that everybody has to simulate very, very exactly the same result. Okay, so it has to be very deterministic, and this is not that easy to achieve. So the other question that you might have is the fact that you do have 100 millisecond latency between the time when you send your command and when you process it. It may even be two loops. You might have to wait through a second loop, so you're processing this current set of commands, recording a set of commands, waiting for the next set of commands. Somewhere in there, you're between 100 and 200 milliseconds. And so you might think that that's kind of a long delay, and it potentially is. But for most of these games and for most of human reaction time, it's fine. One of the tricks that we can do is the same thing that we sort of talked about before, or that we may have talked about before, depending on which lecture you've listened to, in that we can hide a lot of things in the UI. And so we're in a game like this where we know we're going to have to do pathfinding, where we're going to have to add a lot of intelligence. When I say I want to move this character from here to, say, over here, he's going to have to do some pathfinding. He's going to have to move through a crowd, maybe do some crowd prediction as well. And there's more than just he can immediately start moving, right? And so you kind of get used to the idea that you've sent the command and you don't actually see the character start animating right away. But in the UI, we put a little indicator over here, wherever it is you clicked, to say the system knows that you clicked there, and we're about to send that command. But your character, is a human person, and you might imagine, and then they are going to take a certain amount of time to hear, recognize, and process your command and start working with it, right? And so you kind of get used to when you're playing games like this, the characters not necessarily as responsive as they are in, say, an FPS or even like a Street Fighter type game, where every action is almost immediately tied to your button. You expect some time, and of course, it even takes some time for them to start walking. So there's other tricks you can do, like you can actually have them start sort of walking in the right direction, and then they fix things so you sort of predictively start moving. But even without that, there's a lot you can do to hide things inside the UI, just to register that you've clicked, to register that you've started an action. Another one is, when you're doing an advanced move, you will start the VFX immediately to do that move, and then the move catches up with the VFX or something like that. So again, there's a lot of ways to sort of hide things hide this kind of latency, and so it works well for the networking as well. So if we're having to wait for 1 to 200 milliseconds for the network to actually allow us to move forward with our processing, we will also hide that in networking. That doesn't mean we have to hide, the UI itself is still going to run at 60 frames per second. All of our animations are running at 60 frames per second. It's really only the sort of simulation, the processing that we're doing in the background that is running at that slower rate. So let's talk about the breakdown in determinism. So it's all pretty much surrounding the floating point simulation. So again, we talked about this with physics simulation and the fact that there are small errors that creep in. So you require a certain level of precision in order to do the kinds of physics simulations that we would expect at a certain level. And so we do these Eulerian jumps, these small fixed point jumps at the smallest level, which increment error over time, and those errors creep in. And we could do things like we'll use linear dampening to reduce the amount of errors that we're seeing. We can deal with these errors, especially when it's on a single machine and we don't necessarily care that we're trying to synchronize. And so we say, we will damp out some of the errors. We will reduce some of the noise that comes in. And potentially, that kind of thing could work, but it's so hard to predict with networking because you can't see the other side really. Even when you're debugging, even when you're the programmer, it's very hard to look at, say, two machines at once, or even two machines that are far enough apart that you're seeing the kind of latency issues that you're going to run into with the real game. So there's a lot of problems with that. So the better answer is if you want determinism, you can't trust the floating point system, and it gets worse than that. There's differences between, say, the way you're going to get floating point results on Windows versus Mac, because the order operations, and those cause minor differences in the floating point operations. There's also differences between AMD and Intel. So even if you're both on Windows machines, 64-bit Windows machines, if somebody has an AMD and somebody has an Intel, you're still going to get different responses, and so it's very challenging. So the one place that we can actually start to get predictable results is from the integer arithmetic. So the trick there is that we use what's known as fixed point simulation or fixed point arithmetic. And that is that we're actually using an integer to represent a floating point value. It is still an integer, but what we've done is taken our floating point value, multiplied it by, say, 2 to the 16th or 2 to the 32, which sort of shifts the bits upward into the upper region. It'll also squish the highest level of bits, but let's not worry about the details of that too much. We essentially just multiply our floating point value, and then we turn it into an integer. So we truncate any part after we multiply it by some large value to the 16th. We truncate the rest, and then we keep that number, and we do all of our math with that fixed point number, with that large integer that represents a much smaller floating point value. So we can do our adds and our subtracts, and those work just fine. We do need to fix things like multiply and divide a little bit. There's some specialization that you have to do in terms of managing those, as well as like exponent and square root. So there's quite a bit of work involved in building a fixed point simulation. Hopefully you could do that once and then you're done, but it is there, right? And so of course, it doesn't mean that you have to stop using Unity. So Unity still is floating point when you're representing your position and rotation. You can divide your fixed point value back by the 2 to the 16th or 2 to the 32, whatever you did, to get back to a float in order to render. So the graphics card is also going to use floating point values, and you don't care about the render, right? So if you're, these slight errors, the reason that we don't care about them normally is a slight error is a small shift in a pixel. It might even be a sub-pixel difference, and so you wouldn't notice it. So these kinds of errors that might creep in aren't going to really present any differently on the screen between the two systems. Maybe if you actually did a pixel by pixel comparison, you might notice pixel differences or something based on the fact that somebody's fixed point value turned into a float that actually lost a small amount of precision. But most likely you wouldn't really be able to see any difference. So we go back to floats for the visualization. So we send floats into Unity, we send floats into the graphics card, and everything's fine, but all of our fixed point values remain within our simulation. And so if you really want to look at how something like that is done, there was a representation specifically for Unity by the guys who did, the team that did Deserts of Carrick, I'm not sure I'm pronouncing that correctly, where they actually built a deterministic simulator underneath Unity in C#, completely sort of separate from Unity, and then they read, and really all they're doing is forwarding commands from the interface that Unity is taking and putting them into their simulation, and then taking the positions and rotations out and passing them back up to Unity in order to actually do the value. But if you want to dig into that, then you have this YouTube video here to look at that. Okay, so moving on, let's talk about asynchronous send. So now what we're saying is we're no longer carrying the fact that other people are there, right? So we're looking at our game loop. We're going to run our game loop at the rate that we're going. So again, this is kind of our standard gameplay loop. We've looked at this many times now, I think. And so we have the player input. Actually, I didn't create a loop out of it, right? So after we render, we come back up. We have our player input, we have our simulation update, we render, and then we come back and we take the next frame and get more player input, more simulation update, and more rendering. Every 25 to 50 seconds, we're going to capture the current state of our player, and that's our player character, right? So, in the case of an FPS, we have our one player that we're controlling in a third-person shooter. We still have only the one character we're controlling. You might consider other cases where you might not have one character, but you still have, say, a representation of one character. It might be, I don't know, like some buddy pair, that two characters that sort of act like one, right? You can still treat them as one state. But the point is that you have the one thing that the human is controlling, and every, however many milliseconds, you send a new update to say, here's the new state. This is the one I'm going to send you. So this has things like my position, my rotation, probably where I'm looking, almost everything that I need to pass over so that you understand exactly what I'm doing currently, right? Again, this comes down to we need to know exactly where you are to within 25, 50 milliseconds. We can't send more than this, and we'll look at why, because the bandwidth starts to get a little bit too much. But we want to send as much as we can so that we can get the information that we can. That might include actually sending the current animation clip that we are rendering, or that we're animating, and our offset within that clip. And so that as we're moving through that clip, we know exactly where we are in terms of the animation. We might even send hitbox positions. We might not need to send either, right? And so we're now no longer caring about determinism, but our animation cycle might actually be fairly deterministic given our position and rotation. We might also send, say, velocity, acceleration, things like that, if those are useful. And oftentimes they are, and we'll see why. So given that kind of information, if, say, we had a blend tree within Mechanim that knew how to place our feet entirely based on our current velocity, we might actually not need to send our current animation. But in a lot of cases, it's probably still useful to send that information because you don't know exactly when they click the key to start firing or something like that. Those are things I left out of here too. So the fact that we started firing or that we stopped firing, all this kind of stuff, will still help you sort of capture that information. You need to do things like, did you fire off a missile and whatnot, and we'll look at that in a little bit here too when we look at the rollback. Okay. Again, so the hitbox positions are probably based on what your animation is doing, but if there's, for some reason, they're not necessarily synced exactly, then you would need to probably send those as well. So the state broadcast could be pretty large. Usually it's on the order of, say, 500 bytes at most, maybe 1K. But we'll look at an example, or we won't get into a specific example yet. That'll probably be the next lecture. But we'll talk about what the bandwidth cost implies. Okay, so this is our side, right? So we're just talking so far from our standpoint. We're just running our game loop, and whenever we feel like it, we're going to send out a state broadcast. Not necessarily whenever we feel like it, but at a reasonable time frame. Everybody else will be giving us their states when we get them, right? So whenever they feel like sending us states, we're going to receive some. And then we're going to need to queue them and save them, and then keep track of that queue. And then when it comes time for us to update, we go and look and say, okay, give me an interpolation or extrapolation of that other player's state so that I can use it as part of my simulation. Okay? So that's the gist, right? We've got this gameplay loop. We're sending out our state, we're receiving states from other players, we're keeping track of those states, and then we're trying to either interpolate or extrapolate from that queue of states into a specific state situation for every other player within our simulation, and then we can respond to it and things like that. Right. Note that there's probably no sense of authority here, and I actually didn't talk about the cheating issue over here. There's a possibility, because everybody knows about where everybody else is in a deterministic simulation, it actually becomes hard to guarantee fog of war. So that's one of the chief cheats. But there are probably some results, some more recent results, since again this is kind of an older result. So the primary issue with cheating here is that nobody has, so you only do get the updates of other people when they send them to you. So you don't actually know anything about where anybody is until they decided to send it to you. So you can't know ahead of time where somebody is, or you can't necessarily do things. Of course, you can do wall hacks and things like that, where you can look through walls that you shouldn't be looking. The other one is that you don't have authority, and so you can claim things about your state that everybody else doesn't. So I'm not really going to go into anti-cheat behavior. That's kind of more scope than I want to deal with, but I'll leave it to you to kind of look into that. So one of the two problems are that you can, of course, get the wall hacks and things like that, where you can see through the walls, a little bit like breaking fog of war. But the other one is that you can actually lie about your state. All right, so if you're sending the simulation state update, then you can lie about it. Okay, so let's talk about bandwidth. So original Doom was probably only about 70 bytes. However, more modern games were sending a whole lot more data because we have a lot more data to send. Original Doom was really only sending the position and rotation. In fact, it was only sending one angle of rotation because that's all it needed to send. Because you couldn't look like up and down, for instance. But given these 500 bytes, if every 25 milliseconds we're going to send 500 bytes of data, that means that we're sending roughly, or exactly, probably more like roughly, 40 states per second, which is around 20 kilobytes that we're uploading. And that is probably fine, right? So 20 kilobytes is probably okay, unless you're on a 28.8 modem, in which case you may have some problems. But if you're on a LAN or something, definitely no problem. And most people at this point have a pretty decent upload rate that at least will cover this. This is only about 2 megabits upload, I think. No, it's a 0.2 megabits upload. So I guess I'll come back to that. So the megabit comm rate, when you see that, so if you have a 10 megabit line, then you divide by 10, and that tells you how many megabytes you have. That's because there's a start and stop bit on every byte that's sent. So there's 8 bits plus the extra 2 for communication, and so that's why this ratio always seems a little bit off, right? You don't necessarily divide by 8. You actually do divide by 10 in this case. Okay. So if we have 16 players, then if they are all sending us 20 kilobytes, that means that we're going to be getting 320 kilobytes from all of those players. And that means that we need to be downloading that many kilobytes every second in order to keep up. And so that's a 3 megabit link. If you have a 10 megabit link and somebody else is downloading Netflix and somebody else is downloading YouTube or watching YouTube, you might start to lose this 3 megabit link, and that's why you lag even at this level. Okay? So that's kind of where these things start to become troublesome, right? If we go to 32 players, we're now needing a 6 megabit downlink. 64 means we need 12 megabits, and then Fortnite, 100 players, means we need around 25 megabits, right? Not exactly, but close. There are ways that we could probably optimize some of that network requirement. I'm sure Fortnite is doing the best they can, especially there is an LOD aspect where you can actually keep track, especially in a large enough field, of the fact that there aren't probably 100 players immediately around you that you need to simulate that accurately, right? Not to the point where you're being able to incorporate them into your simulation. You might not actually care, other than perhaps maybe audio events or things like that, and you can actually send those on a separate channel. Anyway, not to get into the details, let's get back to just the high-level discussion. So there is a lot of bandwidth going on. This is even worse. So again, this is why it's almost a different networking style entirely, because in the RTS case, we have way more than 64 characters on the screen. There's no way we could send this much information about 64 or even 700 to 1,000 total units if you're having a very large RTS battle. And so that's why there's a real difference between these, because the scale of the number of players is totally different. And of course, if we're talking about an MMO where we've got thousands of players, the scale is off the charts, and there's no way that anybody could download this much information at that speed. So the final thought here is really just that if you look at these bandwidth requirements, it may seem like if we're only sending, say, 40 to, even in this case, we're only doing about 20 frames per second, so somewhere between 40 and 20 frames per second in terms of the state updates. Those are some fairly large gaps, right? We don't really want to run our simulation at that rate. You might be thinking, I wish I could send every 15 or even 16 milliseconds so that I could get 60 frames per second on my simulation, and everybody's running at the same rate. The data requirements would start to get too high, right? So maybe you could do it in the current world with, say, only 8 players or something like that. And maybe something like Street Fighter, you probably could start to, you really only have 2 players on the screen. Maybe you can get away with sending a whole lot of state every, as fast as you possibly can, and you hope that the latency, the time that it takes to actually send the data back and forth is low enough that you can do a Street Fighter. I think you're still going to run into problems there because, we're sending this data, but there's also the latency of the network itself, and usually that's on the order, it's not bad, especially if you're, within the same continent, you're in the continental United States, or you're even talking to Canada, you might be around 50 to 60 milliseconds of latency. That's on top of a delay like this. And we'll look at that. We'll look more into this whole latency issue in a minute. But of course, if you were trying to play, if you're in the U.S. and you're trying to play with China or you're trying to play with Korea, your latency is going to be much worse. Now, if you're on a LAN, you're great. Your latency is on the order of like 5 to 6 milliseconds, and that's pretty fast. And so you can probably actually get reasonably real-time rates at that point and still be within 60 frames on both sides without really any noticeable latency. Okay, so given those latencies, here's what that looks like. So let's say everybody, we have no problem with the initialization time, even though there are some discrepancies there that will happen. But we're going to assume that everybody started at exactly the same moment. Now, that means that this player will probably send the remote player is probably sending their initial 0 state at that 0 time. If we've got a 50 millisecond latency, just again, standard for if you're somewhere within the US, it's a pretty decent value actually. 70 is kind of a normal max, so you might even be as far as 70. If you go anywhere above 100, then somebody's probably broken something and you need to fix it. Or they need to fix it and they're worried about it. But 50 to 70 is probably there. So let's use 50 because it's a nice value. So that means that this state, even though it's here, we've moved forward almost 4 frames by the time we see it. Right? Actually, we moved forward exactly 4 frames, and we're into our 5th frame before we see their first one. And the next one that they're going to send is actually skipping forward, so it skips a frame, and then we see it the next one, and so on. And so we're already sort of way behind each other, right? We're behind by either 4 or 5 frames at any given moment. So we need to deal with that. So this is where the interpolation comes in, or the extrapolation. So we have a couple options. Well, actually, so we have a couple options, and we have another problem. The other problem is, again, that there's a large gap between this, right? So the fact that we're only sending 20 frames per second in update time, or even 40 frames, whatever, means that there is at least 1 step in between, or maybe even 2 steps in between that we're skipping over, right? And so if we wanted to start rendering, doing that simulation update, if we're just using this frame, it might look like they're frozen for 2 frames. And that's not great, right? So we don't really want to see our remote players looking like they're frozen or stalled out or whatever. We want to see them look like they're moving as smoothly as we are, even though we might not be sending as many updates, right? So even though we're sending 20 frames per second, or even as high as 40 frames per second, we're still going to drop some frames. We need to figure out how to simulate these in-between frames. So we've got 2 ways to go about it. Okay. So given that we're going to get this frame, and that we need to at least do the frame update, we'll deal with the latency issue in a minute here. Then in order to render this frame, we could extrapolate our position, right? So here's what that looks like. If I'm getting a position at time 0, so again, this is at time 0 here, and I also have a velocity from that player. So that's again something else that we have to add to our state in order to capture all of that. So I say not only is my position here, but I'm also heading in this direction at this speed. So go ahead and try to fix that, right? So if I want to figure out where I am 13 milliseconds ahead of that, and again remember that it's going to be 25 milliseconds before we get the next state update. So we have to figure out how to extrapolate a full up to maybe as far as 25 milliseconds in order to capture whatever frames. Then we multiply the velocity. It's a little bit like the standard physics update anyway, right? We were even looking at that with the optimization that we do gravity multiplied by delta time. In this case, our delta time is however far we need to extrapolate out. So our delta time is 13 milliseconds. We multiply that by our velocity and we get a positional offset. And now we know what our extrapolated position is at 13 milliseconds. The problem is the simulation on the remote side, our remote opponent may have sent a certain time in a certain direction here, but they most likely changed direction somewhere in here, right? And if it wasn't this state, it's the next state for sure. They're almost never going in a fixed direction at a given time, and they're constantly changing directions in between. And so if we extrapolate, we often run the risk of overshooting, right? And so we will overshoot where we think they are based on the velocity they sent, and then they're in a totally different location, and we have to correct for that. Correction is not necessarily an issue. Usually we can just pop them back, or we can even just sort of interpolate between our predicted position and their new position and sort of fix that over time so that it's not quite as rough as a pop. And so that looks like what we refer to as rubber banding when you see that kind of effect. But it is a problem. So extrapolation can be a worse problem for those kinds of things. The way we avoid that kind of problem is that we use interpolation. So to interpolate, rather than extrapolating from time 0, we now wait until we see the next state offset, whatever that is, in this case 25 milliseconds. And now rather than extrapolating from time 0, we say, well, we know exactly where they were at this state. We also know exactly where they were at this state. So we just use a simple linear interpolation, and it doesn't necessarily need to be a simple linear interpolation, but it usually is, because there's no reason not to. The error is so small. And by the time we get over here, we know exactly where they were. So as long as we're pretty close with anywhere within this window, then there's not really much reason to be any more accurate than that. So what we do is we take the position at T25, so the position here, we take our position at T0 up here, and we figure out what the line is between those two, and then we figure out how far along the line we are again. So 13 milliseconds is our example, 25 milliseconds is the total. That gives us a ratio. And so rather than moving through like a delta time and velocity, sort of like we're actually getting a pseudo velocity here, and then we're using this to essentially multiply us over. But in the end, this is a standard linear interpolation that we're looking at. We've seen this many times in many different ways. A standard linear interpolation that moves us somewhere between here. And so we can interpolate. So if you're following along carefully, you are noticing that we were already talking about being delayed at this time. Now we're talking about this time as well and adding an extra 25 milliseconds. So we're now really talking about if we want to interpolate and we're waiting, we're actually interpolating 75 milliseconds late. And we make it worse than that. We actually go a full 100. So instead of worrying about the fact that we are behind, we make it worse and make sure that we can interpolate. So we generally will wait 100 to 150 milliseconds before we start simulating a remote player. Now the reality is that people don't move that far in 150 milliseconds, right? So if you're moving at around 6 feet per second, you're going to move 1/100th of that, which is around a few inches. Okay, so if I see you as being off by a few inches from where you are in current time, it may make a huge difference in the sniping, and we'll look at that in terms of rollback. But it's not actually going to make a big difference in most cases, because 6 inches when you're trying to shoot sort of ahead is really like maybe half a head's distance. And so as long as you're shooting toward the center, and especially if you're shooting at the body or something, there's not a huge difference, right? And so the discrepancy might be your choice. Really comes down to, say, whether you were fully behind a wall or not. And often what we do is, if there is any discrepancy, we will accept the shooter's perspective, because they're the ones who can really see the difference between the discrepancy. The remote player, the person who's being shot at, can't actually see whether they were fully behind the wall or not. Now, in some cases, they might know for sure because they were sitting partially behind the wall or whatever, and they figured I got shot slightly, in the head where I shouldn't have been because I knew where my head was. I'm not sure. But usually you're not looking in the right direction to see your own body, especially in FPS, right? You're looking where your camera's looking, and the shooter can see your whole body and can see where they're shooting. And so if there's any discrepancy, you trust the shooter, and you use rollback to determine exactly where everybody was at every position if you need to check for cheating. Of course, right now we're saying that we don't have an authority, and so we'll just go ahead and trust the shooter. But again, cheating is going to be out of the scope. Okay, so just to review, we have a 50 millisecond latency before we even see the frame, but we go ahead and wait an extra 50 milliseconds beyond that in order to make sure that we have the next frame in our queue, well within our queue. So in fact, we might even have two of these frames within our queue. And when we talk about protocols, we will address why, because we may actually lose this frame for some reason. So it gives us a chance to get this frame if we lose this one. Otherwise, we have to start extrapolating. But as long as we have at least two positions within our queue, two state updates from the remote player, we can interpolate between those two states. And so that's why we wait. So we actually wait 100 milliseconds or more in case we want extra redundancy. So we might even wait as far as 200 milliseconds. Depending on the game, that might actually be okay. It's also worth noting that you might have to wait longer. So if we're only sending every 25 milliseconds and we're trusting in the 50 millisecond latency here, then we're good. Unfortunately, we do get some hiccups where some players, even though most of the time they're getting 50 milliseconds, sometimes they'll get 100 milliseconds on a certain packet. Sometimes they'll get even as high as 250 milliseconds. So if you're not waiting long enough, then you will, those packets may have actually showed up, but you didn't wait long enough, and then you thought that they never were there, and so maybe you started falling back to extrapolating from that point. So extrapolation is always kind of an option and always the fallback if you've waited long enough and you're not getting that other state that you can interpolate between. But generally, we prefer the interpolation because the amount of error that we're going to accumulate by linear interpolating between these two positions is almost irrelevant. And having this extra information about exactly where that remote player said they were at each of these time steps is valuable for determining that. Again, as always, if you are walking through this and there's any confusion, please do send email or find me at the office hours time to talk through some of this, especially if you're actually trying to implement this yourself. It's pretty heady, but when you get it working, it's pretty slick. It's pretty great to see apparently zero latency or imperceptible latency, but very, very smooth movement from the remote end. Okay, so rollback is the other big piece that we have to deal with in this case. There's a great video on from the 2017 GDC for Overwatch where they talk about the way they do all of this stuff, including the interpolation, the backwards in time, and all that fun stuff. Rollback is, one case we talked about is resolving the cheat scenario where we want to verify exactly where everybody was to the precise details so that we can determine whether or not a snipe shot was actually successful. Again, generally what we're going to do is just trust the shooter and the fact that you were actually 6 inches off, and maybe you really were behind the wall according to your perspective, and the shooter saw you at 6 inches to the left of the wall and shot you. It's really almost a timing issue, right? Because you were 6 inches to the left of the wall at some point. It's just at a different time. Anyway. But this is a case where, let's say that there was some kind of interrupt command. So we've mostly looked at our perspective, right? So I've got the me here versus the remote player. Well, I could be doing something to the remote player, but the remote player is also going to be doing something to me. So let's say that at this time frame, at this 64 millisecond time frame, the remote player does headshot me or shoot me in the head, or some other thing that really should stop me from whatever I was doing forward, right? So let's say I was doing some cool, super attack, and this is where it comes into Overwatch, where you can do these great big special moves or something, but there are ways to interrupt them. This sort of thing becomes even worse when you're talking about a Street Fighter or whatever, because a lot of those are actually interruptible kinds of attacks. And so again, this kind of delay is a nightmare in those scenarios. I don't know how anybody can actually pull those kinds of things off. So okay, at the 64 millisecond time, the remote player has done something to me that interrupts my future movement. I don't know about it until here. Okay, this is again only a 50 millisecond delay. It could be worse. So for the next 4 frames, I'm doing things as though I'm not dead, and yet I'm probably dead, right? So there was a headshot here. I should be dead. I shouldn't be able to do these 4 things. So what do we do about that? Well, we start keeping track of everything I am doing at every moment in order to be able to roll it back. So what we do is, this is different than the state that we're sending out to the network. We are keeping track both of my state and my input at every one of these time steps for a certain amount of history. It doesn't need to be the entire history of the game, although we could use it for replay if we really wanted to. But we keep track of enough history so that we can roll back far enough in time to something reasonable. And again, far enough in time, maybe as far as 200 to 250 milliseconds, but maybe beyond that, we probably don't need to keep a full window. We could even keep a full 1 second window. And what we're really only talking about is, in 1 second is maybe around 60 frames of history. So 60 frames is not too bad. It's too much for me to draw on a presentation slide, but it's not too bad to store in memory for both your entire state, which is 50 to 500 bytes or so, as well as your inputs, which are probably just tracking your key presses or your mouse movements, or maybe your joystick movements if you're doing that. So not a whole lot that you have to keep track of. And so what we do is then this whole scenario. Okay, so we've got this interrupt that happened down here. They were operating on an interpolated state, so it's worth noting that the state that they were operating on was actually this one way up here. So again, I didn't call this out properly, but the remote player was operating on a rollback version of me, a 100 millisecond old version of me, and then I don't know about this interrupt action that they pulled on me until much later. Okay, and so what we have to do is we have to roll all the way back to the point at which they were, say, killing me, right, way up here, and now we have to roll it forward to address the new alternate timeline. Okay, so in the case where all they did was maybe interrupt a move, so I was doing a power move, not necessarily killing me in this case, but I was doing a power move, all of my inputs end up probably just getting ignored through here, because whatever my inputs were all about doing this cool special move that I was doing. And so they all have to be ignored. Maybe I was continuing to move through space. If I was shot here, it's actually much easier, right? We roll back the time, and then really I'm just dead. So we're just playing. The only difference is we're ignoring all the inputs, and we're playing like a death animation from this time. And so there's a small hiccup, right? So I was actually seeing this information. We play it forward. We don't actually play each of these frames. What we do is we speed through these frames in quick time. So we say, the new state. So we had a state that we recorded into our database over here. And we update that state to say, okay, here's the modification, here's the interrupt that happened at this time. Now play forward and recreate those states and update the state history with each of those new states based on this original changed state, right? Again, we're sort of rewriting history at this point in time and then playing it forward with all the inputs. So all of my keyboard presses continue to stay, but they might not matter, right? And so depending on what this new state is, my keyboard inputs might do something weird. And then I catch up down here, and so the next frame that we play, this 100 and whatever it'd be, I can't remember now, it'd be 16 from that, 138, I guess, 128, would be, that frame is the new one. And so that's the one that's updated, and it's now the frame that came from the alternate timeline. But now that's our future correct timeline. So we corrected our state history, and then we're also playing forward from here, and it's kind of synced back in, right? I didn't draw all those lines, but they're there. Okay, so again, before I go too much further, we have the interpolated state they're responding to. They interrupt me in some way, and then I have to rewind that and play forward an alternate history and update. So we can use that both for these interrupting kind of cases. So it's when the other player is breaking me. So everything we were talking about up here is really me understanding where all of the remote players are and being able to deal with all the remote players, right? Where I want to shoot, where they, where they are in space, whether or not they're shooting, what their current hit points are, or whatever. But when it comes to, and most likely they're telling me whether or not they're hitting me, right? Again, we trust the shooter in terms of who the reality of the situation of the game. And then in the case of rollback, we use that when one of these like killer moves happens, when any kind of interrupted state happens. You can also, I mean, there's even some cases where some games will allow you to knock somebody over or stun you, so that you're not necessarily dead, but you or you're given some kind of weird alternate effect that maybe screws up your controls and swaps left for right or something like that. So all of that can be handled with this kind of interrupting state by altering the state history. It again can be a little bit confusing to set up, but it's a great resource for when you want the kind of gameplay that can deal with that. Again, hopefully, I'll speak now that we're kind of to the end of this. I'll speak again to Street Fighter kind of games. The Street Fighter games are all about this kind of interrupt and blocking and countering and so on. And so if you look at these kinds of delays, it would be very hard to make a game that is constantly sort of in a rollback state. So I'm always impressed when I see some of the results that come from that, but I also don't know that I've ever seen one that works that great across like the normal internet. Of course, it can be fine in the LAN, but this is why those kinds of games start to become difficult. The nice thing to note is that as the networks start to become better, and we've already seen this where this bandwidth requirement is way back up here is kind of high, but it's not unreachable anymore, and so we can actually start to get to 100 players, which seemed unreasonable even as far back as 20 years ago, when you might have 100 units in your RTS game, and that even for that it was too much to send across, and so you still need to do the group selection. So as the networks get better and faster and stronger, we will see more and more opportunity to work with latency, or to work within the framework of latency, but we will never be able to get rid of it entirely. We might be able to get it from 50 down to 5, even within the United States, so everybody feels like they're on land. But of course, there starts to become speed of light limits and things like that. Okay, so the last thing I want to talk about within this lecture, and then we'll actually get into in sort of part 2, we'll go into the actual network structures that are available, the way you actually send messages. But to kind of lead into that, let's talk about the way these communications work. So you have probably heard that UDP is the thing that you use to send messages. And the reason for that is that although the latency is exactly the same for a single packet coming from both TCP and UDP, what has to happen before you necessarily get the packet registered as receiving is that you actually have to get the full ACK gone through. So what happens is that if I am the sender and I send my first message, and I have this SYN, and then the receiver sends a SYN ACK, and I send the ACK that I received that, I will then send the next packet. I will, let's say there's 4 or 5 packets in a row, and I missed one of these messages, either the sender didn't see my ACK or I didn't see his ACK, then I will not show you this message or any of these other messages down here, even though I may have seen all of the ACKs for these other messages further down. Because I was missing this one, I'm going to wait, because TCP guarantees both that every message will be received and that every message will be received in the same order. And we don't necessarily care about that. So you'll remember that up here, when I was talking about these states, we do want, potentially for interpolation, we want to make sure we get a later state, but we don't necessarily care that it's exactly this next state. We might be fine with, well, okay, we missed this one, but we got this one, or we even missed these two and we got this 75 millisecond one. We can still interpolate from 0 to 75. The error is not as good, but it's not nearly as bad as having to extrapolate. And if we started having to wait until we got all of those ACKs and SYNs back, then we're having to wait potentially up to 3 levels of latency. So for 50 milliseconds, that might actually be a full 150 millisecond latency. Now for things like streaming and for video, we actually do care that we're getting everything in order in the way we said, because you want to see the first frame of your video before you see the second and third and fourth frame, and so skipping frames in video can be a problem. So that's why TCP exists, right? And in the case of sending files and all kinds of things, TCP is the right solution. But in the case of sending the state to our games, we don't necessarily care, right? And we don't need all of this stuff. The one case where you might actually start to look and say, well, maybe I do use TCP is way back here, right? So if I am doing an entirely deterministic simulation, I might be willing to allow for TCP up here because I'm only waiting for one broadcast and I am willing to wait up to 150 milliseconds. So the fact that I want to make sure that I get every command in the order that the player sent them is probably good. Now we can do a few things with UDP to guarantee. Generally what we'll do is continue to send the same, if we want a semi-reliable kind of result, and the libraries that we're looking at will do that. Then we can resend messages. So I guess I haven't gone into UDP. The difference with UDP is there is no acknowledge, right? So there is no guarantee. You simply send whatever message you send. You can send a request, you can send a response. Your request might not get there, your response might not get there. There are many places where those messages just sort of disappear. And in fact, it actually comes down to, when a router somewhere on the network is busy enough, it will simply just drop packets. And usually, what it turns out is, if it's busy enough with TCP traffic, it will drop all of its UDP packets. And so UDP packets, that's the one case where UDP becomes a problem, is that TCP is often not dropped if there's any UDP packets available to drop. If it's all TCP data, then it has to choose to drop some of the TCP packets. The reason for that is that most the people who write router software know that if I'm going to drop a TCP packet, I'm going to be seeing another resend of that, because if I don't see the ACKs, if I don't see any of these messages, I'm going to resend whichever part of this was missing, right? So if I didn't see the SYN ACK, I'm going to keep sending the SYN until I see the SYN ACK. And then if I send the ACK, or if I see the SYN ACK, if I don't see the final ACK, I'm going to keep resetting the SYN ACK, right? At a certain point, you might wonder, well, do I actually care about the ACK? I don't actually care about the final ACK. If I see a SYN ACK, I send an ACK. If I see a SYN ACK, I send an ACK. At some point, this guy will stop sending the SYN ACKs when he actually gets that. Anyway, so yeah, with UDP, you don't really have any guarantees. But if you're sending so many states constantly, if you are sending a state every 25 milliseconds and you're sending 40 of these every second, if you drop a few of them every second, it really doesn't matter. Your interpolation is fine, especially since you're not going to accumulate any error from the remote player by dropping these interim packets, right? So if I drop to the 25 millisecond or the 50 millisecond, I still know exactly where the player is at this time, right? And even more, if I get these out of order, if it turns out that for whatever reason something was rerouted, and so again, TCP will guarantee that. It will not let me see any of the later packets until I get this one fully resolved, this earlier packet. If in UDP I was for some reason to get the 75 millisecond packet, and I later get the 25 and 50, I'll just ignore those, right? So for whatever reason, these guys were super delayed, and I got the 75 millisecond one. I've already started interpolating according to that. There's not really a good reason for me to pop in and try to use these packets. And so that's why we tend to trust UDP more. Again, it's probably the case, although I have to admit I've never written a synchronous or deterministic simulation. I've usually only done this kind of asynchronous, even when I'm doing sort of semi RTS games, because you can get away with quite a bit with even this by lowering your update history. But yeah, so in RTS, I might actually start to consider, if I'm really only sending commands, using TCP just to guarantee that was there. But we can do a similar kind of SYN and ACK thing to some degree with UDP by mimicking that. Okay, so that's it for this lecture. Look for part 2, where we'll actually go through how we get a hold of a communication protocol. And thankfully, we are not writing just raw packets. We're usually getting a lot of help from these systems in both connecting to the remote systems and sending packets, and even doing reliable transfer on UDP if we really need to. For cases for things like special moves, or the fact that I'm firing off a missile or something like that, at a given time, I might actually care that that is a pretty reliable message versus just the normal state updates that I get. So we'll look at a lot more of those details in terms of the actual systems when we get to those.